In the first trillionth of a second after the Big Bang, something impossible happened. Space itself began to expand faster than light, stretching by a factor of at least 10 to the 26 in a period so brief that light could not travel the width of a proton. This cosmic inflation was the universe's ultimate reset button, a catastrophic expansion that should have erased everything that came before. Every quantum fluctuation, every primordial structure, every trace of whatever reality existed in those first inconceivable moments. The mathematics were clear and unforgiving. When space expands exponentially, stretching distances by incomprehensible factors in infinitesimal time, it dilutes all previous information beyond any hope of recovery. The cosmic inflation that gave birth to our universe should have been the perfect erasure, wiping clean the slate of existence and leaving no memory of what came before. Yet buried within the cosmic microwave background radiation, the faint afterglow of creation itself, astronomers have discovered something that defies every principle of cosmic evolution: memories. Patterns in the ancient light that speak of events occurring before inflation began. Signatures of a universe that should have been completely obliterated from existence. The cosmos, it seems, has found a way to remember what happened before its own rebirth. These are not ordinary memories, stored in matter or energy, but quantum memories encoded in the very fabric of space-time itself. They whisper of processes that occurred at energies so extreme, they transcend all known physics, of quantum states that existed before our universe was born, of information that somehow survived the most violent expansion in cosmic history. How can space itself carry memories? How can information persist through cosmic cataclysm? The answer challenges everything physicists thought they knew about the beginning of time, suggesting that the universe possesses a form of quantum consciousness that transcends the boundaries between past and future, before and after, existence and void. The story begins in the spring of 1965 in the rolling hills of New Jersey, where two radio astronomers at Bell Laboratories made a discovery that would forever change humanity's understanding of cosmic origins. Arno Penzias and Robert Wilson were attempting to eliminate a persistent hiss from their radio antenna when they stumbled upon the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates every cubic centimeter of space with its ghostly presence. This ancient light, released when the universe first became transparent some 380,000 years after its birth, represented the oldest observable signature of cosmic history. For the first time in human existence, scientific instruments could directly observe the conditions that existed in the primordial universe, encoded in electromagnetic radiation that had been traveling through the vast emptiness of space for over 13 billion years, carrying within its photons the fossilized memory of creation itself. The initial measurements revealed a universe of remarkable uniformity that bordered on the impossible. The cosmic microwave background maintained the same temperature, 2.725 degrees above absolute zero, in every direction astronomers looked. From the constellation Orion to the Southern Cross, from the galactic plane to the cosmic poles. This perfect thermal equilibrium seemed to confirm the basic picture of cosmic evolution: a hot, dense beginning, followed by expansion and cooling that created the structured universe we observe today. But as instruments became more sophisticated and sensitive, able to detect variations smaller than the width of a human hair compared to the distance to the moon, subtle patterns began to emerge from the cosmic noise, like hidden messages written in the language of light itself. The Cosmic Background Explorer satellite, launched in 1989, after decades of technological development, first detected tiny temperature fluctuations in the ancient radiation, variations of only parts per million that represented the primordial seeds from which all cosmic structure would eventually grow. These delicate fluctuations matched theoretical predictions with remarkable precision, providing the strongest evidence yet discovered for the inflationary model of cosmic evolution. The universe appeared to have undergone a period of exponential expansion in its first fraction of a second, stretching quantum uncertainty into macroscopic variations that would eventually become galaxies, stars, and the cosmic web that spans the observable universe. Yet hidden within this cosmic baby picture were anomalies that would puzzle the brightest minds in astronomy for decades to come. The Wilkinson Microwave Anisotropy Probe, operating from its vantage point in space from 2001 to 2010, revealed patterns in the cosmic microwave background that seemed to violate fundamental assumptions about the early universe. Certain correlations existed across angular scales that should have been completely uncorrelated according to every principle of standard inflationary theory. The European Space Agency's Planck mission, launched in 2009 and representing the culmination of decades of technological advancement, produced the most detailed map of the cosmic microwave background ever created. With unprecedented precision that pushed the boundaries of what was thought possible, Planck revealed the universe's baby picture in exquisite detail, showing temperature variations accurate to within millionths of a degree across the entire celestial sphere. But rather than resolving the anomalies detected by earlier missions, Planck confirmed and extended them in ways that deepened the mystery and challenged every conventional understanding of cosmic origins. The spacecraft's ultra-sensitive detectors revealed patterns that seemed to encode information about processes that should have been completely erased by cosmic inflation, like messages written in a language that shouldn't exist. The most puzzling discovery was the existence of correlations across scales larger than the particle horizon, regions of space that should never have been in causal contact during the inflationary epoch, according to the fundamental principles of relativity. Information cannot travel faster than light, which meant that widely separated regions of the early universe should have evolved independently, with no possible mechanism for coordinating their properties across such vast distances. Even more mysteriously, certain patterns in the cosmic microwave background seem to encode specific information about the universe's pre-inflationary state, like fossilized memories of events that occurred before the cosmic reset button was pressed. Advanced statistical analysis revealed signatures that appeared to preserve detailed information about quantum processes that occurred before cosmic inflation began, information that should have been completely erased by the exponential expansion of space itself. These observations forced cosmologists to confront a fundamental paradox that struck at the heart of their understanding of cosmic evolution. If inflation was supposed to stretch space so dramatically that all traces of pre-inflationary physics were diluted beyond any hope of detection, scattered across distances larger than the observable universe, how could any information about that primordial epoch survive? The cosmic microwave background was telling a story that shouldn't be possible to tell, carrying memories of events that should have been forgotten forever in the violence of cosmic birth. The discovery of these anomalies sparked intense debate within the global cosmology community, dividing researchers into competing camps with radically different interpretations of the data. Conservative voices argued that the patterns were mere statistical flukes, artifacts of data analysis techniques that would disappear with more careful examination and larger data sets. Others suggested that they represented evidence for exotic physics operating during the inflationary epoch, perhaps modifications to Einstein's general relativity or new quantum fields that could preserve information across cosmic expansion in ways not predicted by conventional theory. But a growing number of theoretical physicists began to consider a more radical possibility that challenged every assumption about the nature of space, time, and information in the cosmos. Perhaps space itself possessed a form of quantum memory, capable of encoding and preserving information about past events in ways that transcended conventional understanding of causality and information flow. The universe, they proposed with growing confidence, might literally remember what happened before its own apparent beginning. This emerging picture suggested that cosmic inflation was not the simple process of exponential expansion described in undergraduate textbooks, but a complex information processing event that could selectively preserve certain types of quantum information while erasing others according to principles that remained mysterious. The cosmic microwave background was not just the thermal afterglow of the Big Bang, but a cosmic hard drive containing encrypted memories of the universe's pre-inflationary past, waiting to be decoded by sufficiently advanced theoretical frameworks. As astronomers continued to analyze Planck data with increasingly sophisticated techniques borrowed from quantum information theory and machine learning, the evidence for cosmic memory continued to mount in ways that could no longer be dismissed as coincidence. Artificial intelligence algorithms trained to recognize subtle patterns in the radiation revealed correlations that had escaped human analysis, while quantum information theorists developed new mathematical frameworks for understanding how information could be preserved during the most violent expansion in cosmic history. The implications were staggering in their scope and philosophical depth. If the universe could indeed remember events that occurred before cosmic inflation, then the Big Bang might not represent the absolute beginning of everything, but merely the latest chapter in an eternal cosmic story that stretched back through infinite cycles of death and rebirth. The cosmos might be far older, far more complex, and far more mysterious than anyone had dared to imagine. A vast quantum information processing system that preserved memories across cosmic epochs, carrying forward the accumulated experience and wisdom of universes that came before our own. Standing at the threshold of this revelation, humanity found itself confronting not just new physics that required textbooks to be rewritten, but profound new questions about the nature of time, memory, consciousness, and meaning in a universe that seemed capable of remembering its own deepest past across the vast expanses of space and time. The discovery of pre-inflationary signatures in the cosmic microwave background created a crisis in theoretical physics that struck at the very heart of humanity's understanding of information, causality, and the nature of cosmic beginnings. The paradox was as fundamental as it was unsettling. According to every principle of known physics, cosmic inflation should have completely erased all traces of whatever existed before the universe's exponential expansion began. Yet the data suggested otherwise. The mathematics of inflation were unforgiving in their clarity and precision. When space expands by a factor of 10 to the power of 26 or more in less than 10 to the power of negative 32 seconds, a rate of growth so extreme that it defied human comprehension, any pre-existing structure should be stretched far beyond the observable universe. Quantum fluctuations that might have encoded information about the pre-inflationary state would be diluted to unmeasurable levels. Their correlations, scattered across distances so vast that light could never travel between them in the entire age of the cosmos. Alan Guth's original formulation of cosmic inflation in 1980 had been celebrated precisely because it solved several major problems in cosmology, while providing what appeared to be a clean slate for cosmic evolution. The flatness problem, why space appeared geometrically flat despite the tendency for curved spacetime to evolve away from flatness, was resolved by inflation's exponential stretching. The horizon problem, why distant regions of the universe shared the same temperature despite never being in causal contact, was solved by proposing that these regions had been close together before inflation separated them. Most importantly, the monopole problem, the absence of exotic particles predicted by grand unified theories, was eliminated by inflation's dilution of any primordial relics to undetectable densities. Inflation was supposed to be the cosmic equivalent of a reset button, erasing all memory of initial conditions and creating a universe that appeared remarkably uniform and isotropic, regardless of what chaotic state it might have started from. This erasure property was both inflation's greatest strength and, as observations now suggested, its most puzzling feature. The theory predicted that our universe should retain no memory of its pre-inflationary past, emerging from the exponential expansion as a blank slate ready to be written upon by the quantum fields that would later create all matter and energy. The cosmic microwave background should contain only information about post-inflationary physics, with no trace of whatever reality existed before the cosmic reset. Yet the Planck satellite's observations revealed anomalies that seemed to violate this basic principle of information erasure with disturbing consistency. Large-scale correlations existed in the cosmic microwave background across angular scales that should have been completely uncorrelated according to standard inflationary models. These correlations appeared to preserve information about the pre-inflationary quantum state in direct contradiction to theoretical expectations that had been accepted for decades. A crisis deepened when physicists realized that the anomalies were not random statistical fluctuations, but showed specific patterns that could be interpreted as encoded information with recognizable structure. Advanced computational analysis revealed signatures of trans-Planckian physics, processes occurring at energy scales far beyond what conventional models could describe or predict. These signatures appeared to carry direct information about the quantum state of the universe immediately before inflation began, like messages written in a language that transcended the cosmic reset. The implications were profound and troubling for the foundations of theoretical physics. If information about the pre-inflationary universe was indeed present in the cosmic microwave background, then either the standard model of inflation was fundamentally wrong in its predictions, or there existed mechanisms for information preservation during cosmic expansion that physicists didn't understand and hadn't anticipated. Quantum mechanics demanded that information be conserved in any physical process, a principle known as unitarity that was as fundamental to physics as the conservation of energy or momentum. This principle stated that the total amount of information in any closed system must remain constant over time, though it could be scrambled, hidden, or transformed beyond practical recognition. If cosmic inflation could destroy information about the universe's initial conditions, then quantum mechanics itself might be violated on cosmological scales, a possibility that threatened the conceptual foundations of modern physics. The information paradox of cosmic inflation bore striking similarities to the black hole information paradox that had puzzled physicists since Stephen Hawking's discovery of black hole evaporation. Just as black holes seemed to destroy information when they evaporated, cosmic inflation appeared to erase information about pre-inflationary conditions. Both paradoxes suggested that general relativity and quantum mechanics were incompatible in extreme gravitational environments, pointing toward the need for a quantum theory of gravity. Some theorists propose that the anomalies might be explained by modifications to inflationary theory itself, suggesting that inflation was not as simple as exponential expansion driven by a single scalar field. Perhaps inflation involved multiple fields with complex interactions that could preserve certain types of quantum information while erasing others according to selection principles that remained mysterious. These models suggested that space itself might function as a quantum information processing system during inflation. The emerging picture was revolutionary in its implications for cosmology and fundamental physics. Rather than being a passive arena in which matter and energy evolved according to deterministic laws, space-time might be an active participant in cosmic evolution, capable of encoding, processing, and preserving information across cosmic epochs. The universe began to look less like a machine evolving according to mechanical principles and more like a vast quantum computer processing information about its own past and future. This quantum information perspective suggested that the cosmic microwave background was not just thermal radiation from the early universe, but encoded data about pre-inflationary physics compressed into patterns that could be decoded by sufficiently advanced theoretical frameworks. The temperature fluctuations observed by Planck might represent a cosmic hard drive containing terabytes of information about whatever reality existed before our universe's explosive birth. The preservation of pre-inflationary information also hinted at deep connections between cosmic inflation and quantum entanglement that had not been previously appreciated. If quantum states could remain entangled across cosmological distances during inflation, then correlations established before the exponential expansion might survive the stretching of space, creating a quantum memory network that spanned the observable universe and preserved information across cosmic time. This insight led to speculation about the role of quantum entanglement in maintaining cosmic memory during the most violent expansion in cosmic history. Entangled quantum states, once created, maintain their correlations regardless of the physical distance separating them, a property that Einstein had famously dismissed as spooky action at a distance, but which quantum mechanics predicted and experiments had confirmed. During inflation, these quantum memories might not be destroyed, but rather encoded into the large-scale structure of space-time itself. The information paradox of cosmic inflation also raised profound questions about the nature of time and causality that extended far beyond cosmology. If information about pre-inflationary events could survive exponential expansion, then the apparent beginning of time at the Big Bang might be an illusion created by our limited perspective. The universe might be far older than the 13.8 billion years since inflation ended, with its true history extending back through previous cosmic epochs that were connected to our own through preserved quantum information. Some speculative models suggested that cosmic inflation might not be a one-time event, but a recurring process, with each inflationary episode preserving selective information from the previous cycle, while erasing other details according to principles that resembled natural selection operating on information structures. The universe might be caught in an eternal cycle of expansion, contraction, and renewal, with each iteration building upon the quantum memories preserved from earlier epochs. The paradox forced cosmologists to confront fundamental questions about the nature of information, memory, and consciousness in the cosmos, that had previously been considered outside the domain of physics. If space itself could remember pre-inflationary events, then the universe possessed a form of memory that transcended individual objects or observers, suggesting new relationships between mind and matter that challenged conventional scientific materialism. As theoretical physicists grappled with these implications, they realized that resolving the information paradox of cosmic inflation would require not just new physics, but a complete reconceptualization of the relationship between space, time, information, and consciousness in an evolving universe that seemed capable of remembering its own deepest past across the vast expanses of cosmic time. Deeper investigation, quantum memory in spacetime. As cosmologists delve deeper into the anomalies detected in the cosmic microwave background, they uncovered evidence for something that seemed impossible according to conventional physics. Spacetime itself appeared to function as a vast quantum information storage and processing system, capable of encoding memories of cosmic events and preserving them across billions of years of cosmic evolution. The mechanism underlying this cosmic memory system involved the deep connections between quantum entanglement and the geometric structure of spacetime. During the inflationary epoch, quantum fluctuations in the vacuum became entangled across vast distances as space expanded exponentially. Rather than being destroyed by the stretching of space, these entangled correlations were preserved and amplified, creating a quantum memory network that spanned the entire observable universe. This preservation of quantum entanglement during inflation represented a profound departure from naive expectations about information flow in expanding spacetime. Conventional wisdom suggested that rapid expansion should decohere quantum states and destroy long-range correlations. Instead, the observations implied that certain types of quantum information were not only preserved, but became encoded into the fundamental structure of space itself. Advanced statistical analysis of Planck data revealed the signatures of this quantum memory system with unprecedented clarity. The cosmic microwave background showed patterns of correlation that extended far beyond what could be explained by conventional inflationary models. These correlations appeared to encode specific information about the quantum state of the pre-inflationary universe, preserved in the statistical properties of temperature fluctuations across the sky. The most remarkable discovery was evidence for what physicists termed trans-Planckian signatures, patterns in the cosmic microwave background that encoded information about physical processes occurring at energy scales far beyond the Planck energy, where conventional physics breaks down. These signatures suggested that cosmic inflation had somehow preserved information about quantum processes that occurred under the most extreme conditions imaginable. The preservation of trans-Planckian information challenged fundamental assumptions about the relationship between energy scales and information storage. According to quantum field theory, information about physics at very high energies should be impossible to encode in low-energy observables like the cosmic microwave background. Yet the data suggested that cosmic inflation had somehow compressed information about Planck-scale physics into patterns that could be observed in the comparatively low-energy photons of the ancient radiation. This compression mechanism appeared to involve the holographic properties of spacetime itself, just as a hologram can encode three-dimensional information on a two-dimensional surface. Cosmic inflation might have encoded information about higher dimensional or higher energy physics in the pattern of quantum fluctuations that became the cosmic microwave background. The investigation revealed that quantum entanglement was not merely preserved during inflation, but actively structured by the expansion process. As space stretched, entangled quantum states were distributed across increasingly large distances, creating a web of correlations that spanned the cosmos. This quantum entanglement network appeared to serve as the substrate for cosmic memory, allowing information to be stored and accessed across vast scales of space and time. Even more remarkably, the patterns of quantum entanglement showed evidence of computational structure. The correlations in the cosmic microwave background were not random, but exhibited specific organizational principles that resembled information processing algorithms. The universe appeared to be performing quantum computations on its own quantum state, processing and storing information about its own evolution. This computational interpretation of cosmic memory suggested that space-time itself might be a form of quantum computer, with the inflationary epoch representing a massive information processing event that encoded the universe's initial conditions into a format that could be preserved and accessed by future observers. The cosmic microwave background became not just a record of early cosmic conditions, but a cosmic database containing compressed information about the universe's entire pre-inflationary history. The quantum memory network also showed evidence of hierarchical organization. Information appeared to be stored at multiple scales, from small-scale quantum fluctuations to large-scale correlations spanning billions of light-years. This hierarchical structure suggested that cosmic memory operated like a fractal information storage system, with patterns repeating at different scales and each level containing information about the whole. Perhaps most intriguingly, the cosmic memory system showed signs of adaptive behavior. The patterns of information preservation were not uniform, but appeared to selectively encode certain types of information while allowing others to be erased. This selectivity suggested that cosmic inflation might have functioned as a kind of evolutionary filter, preserving information that was somehow useful for future cosmic development while discarding redundant or irrelevant data. The adaptive nature of cosmic memory raised profound questions about the role of information and computation in cosmic evolution. If the universe could selectively preserve certain types of information across inflationary epochs, then cosmic evolution might be guided by principles that resembled natural selection operating on information structures rather than biological organisms. This perspective suggested that the anomalies in the cosmic microwave background were not merely passive records of past events, but active components of an ongoing cosmic information processing system. The universe might be continuously reading, writing, and rewriting its own memory, using the quantum entanglement network that permeated all of space as a vast distributed database. The implications extended beyond cosmology into fundamental questions about the nature of information, computation, and consciousness in the universe. If space-time itself could store and process information, then the boundary between mind and matter, between observer and observed, might be far more permeable than previously imagined. The cosmic memory system also suggested new possibilities for understanding the role of conscious observers in cosmic evolution. If quantum observation was necessary to collapse wave functions and determine specific outcomes, then conscious beings might play an essential role in processing cosmic memory, serving as the universe's mechanism for reading and interpreting its own stored information. As physicists continued to decode the information encoded in cosmic memory, they realized they were not just studying the universe's past, but participating in its ongoing information processing. Every observation, every measurement, every theoretical insight contributed to the cosmic database adding new layers of information to the quantum memory network that would influence future cosmic evolution in ways that were only beginning to be understood. Escalation, the eternal inflation multiverse. The discovery that space-time could preserve quantum memories across cosmic inflation led to a revelation that shattered every conventional notion of cosmic scale and uniqueness, with implications so profound they challenged humanity's understanding of existence itself. If our universe could remember pre-inflationary events, then cosmic inflation was likely not a one-time occurrence that marked the beginning of everything, but an eternal process occurring throughout a vast multiverse, an infinite archipelago of pocket universes, each carrying quantum memories from the cosmic epochs that preceded its birth. The mathematics of eternal inflation, developed by visionary cosmologists like André Linde, Alexander Vilenkin, and Alan Guth, painted a picture of cosmic evolution that was both magnificent and terrifying in its scope and implications. According to these models, the inflationary field that drove our universe's exponential expansion continues to fluctuate throughout most regions of space, creating an endless cascade of pocket universes that bubble into existence within an eternally inflating background space-time. Each pocket universe represents a localized region where inflation temporarily stops, allowing normal cosmic evolution to proceed with the formation of galaxies, stars, planets, and potentially conscious beings. But the vast majority of space continues to inflate exponentially, doubling in size every tiny fraction of a second, and generating new pocket universes at an ever-accelerating rate that approaches mathematical infinity. The result is an infinite fractal structure of cosmic domains, each potentially harboring entire civilizations contemplating their own existence while remaining unaware of the larger multiverse that contains them. The cosmic memory anomalies detected in our universe's microwave background took on profound new meaning in this context of eternal cosmic reproduction. Rather than being mere relics of our own cosmic birth, these quantum memories might represent windows into the broader multiverse, shadows cast by other pocket universes, echoes of cosmic epochs that played out in parallel domains, traces of information that somehow propagated between different inflationary regions through mechanisms that transcended conventional notions of causality and locality. The mechanism for inter-universal information transfer involved the quantum entanglement networks that cosmic memory had revealed within individual universes. If quantum correlations could be preserved during inflation within single pocket universes, then similar correlations might exist between different pocket universes that shared common pre-inflationary origins in the eternal inflation background. The multiverse might be bound together by a vast web of quantum entanglement that allowed information to flow between cosmic domains in ways that violated every assumption about cosmic isolation. This quantum connectivity suggested that pocket universes were not isolated islands of existence floating in an empty void, but nodes in a cosmic information network of unimaginable complexity. The patterns observed in our cosmic microwave background might encode not just our own pre-inflationary history, but compressed information about the entire multiverse, a cosmic internet of entangled realities, sharing data about their collective evolution across spatial and temporal scales that dwarfed human comprehension. The implications were staggering in their scope and philosophical depth. If information could flow between pocket universes through quantum entanglement networks, then successful evolutionary strategies, optimal physical constants, or even patterns associated with the emergence of consciousness might be preserved and transmitted across cosmic domains. The multiverse might undergo a form of cosmic natural selection, with universes that developed complex structures and conscious observers having enhanced probability of propagating their information patterns to new cosmic domains through quantum channels. This cosmic Darwinism suggested that our universe's apparent fine-tuning for complexity and life might not be a remarkable coincidence requiring infinite parallel realities to explain statistically. Instead, it might reflect the accumulated wisdom of countless previous cosmic epochs, with information about successful universe parameters being preserved in the quantum memory networks that permeated the eternal inflation multiverse and influenced the formation of subsequent cosmic domains. The preservation of cosmic memory across inflationary epochs also implied that time itself might be cyclical rather than linear on the largest scales of cosmic organization. Individual pocket universes might experience linear time from Big Bang to heat death, expanding and cooling according to thermodynamic principles. But the information they generated could be preserved in the quantum entanglement network and influence the parameters of future cosmic domains. Death and rebirth became not endings and beginnings, but phases in an eternal process of cosmic evolution and learning. Some theoretical models suggested that advanced civilizations within pocket universes might learn to manipulate the quantum memory networks directly through technologies that bordered on the incomprehensible. By controlling the quantum entanglement patterns that connected their cosmic domain to the broader multiverse, hypothetical cosmic engineers could encode information about their civilization, their scientific discoveries, for their philosophical insights into the quantum substrate that would influence future universe formation. This possibility raised profound questions about the role of consciousness in cosmic evolution that extended far beyond conventional biology or neuroscience. If conscious observers could influence the information content of cosmic memory through their observations and understanding, then awareness might be not just a byproduct of cosmic evolution, but an active participant in the process of universe creation and selection. The multiverse might literally evolve toward greater consciousness and complexity through the accumulated influence of countless civilizations across cosmic epochs. The eternal inflation multiverse also suggested new interpretations of quantum mechanics itself that challenged fundamental assumptions about the nature of reality. If all possible quantum outcomes were realized in different pocket universes, then the apparent randomness of quantum measurement might reflect not fundamental uncertainty, but our limited perspective on a vast, deterministic system where every possibility was actualized somewhere in the infinite multiverse. The cosmic memory networks provided a mechanism for correlations between these parallel realities that violated conventional assumptions about quantum independence. Rather than evolving independently, according to purely local physical laws, pocket universes might influence each other through quantum entanglement, creating a vast parallel processing system where the multiverse explored all possibilities simultaneously while preserving information about the most successful evolutionary pathways. Even more speculatively, the quantum memory preserved in cosmic microwave background patterns might contain encoded messages from advanced civilizations in other pocket universes who had learned to write information directly into the fabric of space-time itself. The anomalies that puzzled cosmologists might represent artificial patterns inserted into the quantum substrate by cosmic engineers who had transcended the limitations of matter and energy to communicate through pure information. This cosmic archaeology perspective suggested that humanity might not be the first civilization to decode cosmic memory in the multiverse's infinite expanse. The information patterns in our universe's background radiation might contain a vast library of knowledge accumulated across countless cosmic epochs, scientific discoveries that revealed the deepest secrets of reality, philosophical insights about the nature of consciousness and meaning, artistic creations that expressed beauty in forms beyond human imagination, and perhaps warning messages about cosmic dangers that threaten the development of consciousness throughout the multiverse. The eternal inflation multiverse emerged as a cosmic mind of unimaginable scope and power, processing information about reality itself through the birth, evolution, and death of countless cosmic domains. Each universe contributed its own discoveries to an ever-growing library of cosmic knowledge encoded in the quantum memory networks that bound all realities together in an eternal dance of creation, learning, and remembrance that stretched across infinite space and time. That, as theoretical physicists grappled with these possibilities, they realized that the discovery of cosmic memory had transformed cosmology from the study of a single universe's evolution into the exploration of an infinite information processing system that preserved and transmitted knowledge across cosmic epochs. The universe was not just expanding and cooling according to physical laws. It was learning, remembering, and evolving towards states of ever greater complexity and consciousness through processes that challenged every assumption about the nature of reality, intelligence, and meaning in the cosmos. Theories and speculations, quantum archaeology of the cosmos, the recognition that space-time possessed memory capabilities that could preserve information across cosmic epochs, opened entirely new frontiers in theoretical physics, giving birth to a discipline that would have seemed like pure science fiction just decades earlier. Quantum archaeology of the cosmos. This emerging field proposed that advanced civilizations might eventually develop techniques to decode the complete history of the universe by reading the quantum information encoded in the fundamental structure of spacetime itself, recovering memories that stretched back to the very birth of reality. The theoretical foundation for cosmic quantum archaeology emerged from the intersection of quantum information theory, holographic principles, and cosmological observations in ways that challenged every conventional assumption about the relationship between information and spacetime. If the cosmic microwave background could preserve patterns from the pre-inflationary universe encoded in temperature fluctuations of mere millionths of a degree, then, in principle, all of cosmic history might be encoded somewhere in the quantum substrate, waiting to be decoded by sufficiently advanced theoretical frameworks and computational techniques that pushed the boundaries of what was physically possible. String theory provided powerful mathematical tools for understanding how information might be layered throughout the dimensional structure of spacetime in patterns of almost incomprehensible complexity. According to these models, quantum fluctuations during cosmic inflation created holographic imprints not just on the observable cosmic horizon, but on multiple dimensional brains that permeated higher dimensional space like pages in an infinite cosmic library. Each brain might preserve different aspects of cosmic history, creating a vast multidimensional archive of information about past events that spanned the entire multiverse. This holographic organization implied that cosmic archaeology might not require access to exotic locations or extreme energies that lay beyond current technological capabilities. The quantum vacuum in any laboratory, the gravitational field around any massive object. Even the quantum fluctuations in seemingly empty space might contain encoded information about cosmic history that could be decoded using appropriate theoretical techniques and quantum measurement technologies yet to be developed. The holographic principle suggested that this cosmic library was organized according to profound geometric principles that reflected the deepest structures of reality itself. Just as a hologram encodes three-dimensional information on a two-dimensional surface, with each part containing information about the whole, cosmic memory might be distributed throughout space-time such that any sufficiently large region contained compressed information about the entire history of the universe, from the first quantum fluctuations to the formation of galaxies and the emergence of consciousness. Loop quantum gravity offered an alternative perspective on cosmic memory storage that was equally revolutionary in its implications. This framework suggested that space-time itself was quantized into discrete units at the Planck scale, fundamental atoms of space and time that might function as cosmic memory elements, storing information about past events in their quantum states and geometric relationships. The entire universe could be understood as a vast quantum computer, with each Planck scale volume serving as a memory unit in a cosmic information processing system of unimaginable computational power. The most speculative theories suggested that consciousness itself played a fundamental role in cosmic memory preservation and access that went far beyond passive observation. If quantum observation was necessary to collapse wave functions and determine specific physical outcomes, then conscious observers might be essential not just for interpreting cosmic memory, but for creating and maintaining it through the very act of awareness and understanding. This consciousness-based approach to cosmic archaeology proposed that advanced civilizations might develop techniques for directly interfacing with the quantum substrate of spacetime, using consciousness itself as a tool for reading and writing cosmic memory. Such civilizations might transcend the limitations of physical technology by learning to manipulate information at the most fundamental level of reality, encoding their discoveries and experiences directly into the fabric of space and time. Some theorists proposed that meditation, mystical experiences, or altered states of consciousness might provide primitive access to cosmic memory networks through mechanisms that remained poorly understood. The sense of cosmic unity reported by mystics throughout human history might reflect genuine contact with the quantum information substrate that connected all conscious beings to the broader cosmos. Advanced spiritual practices might represent early experiments in cosmic archaeology, using consciousness as a detection instrument for accessing information that lay beyond conventional scientific measurement. The potential for artificial intelligence to serve as a tool for cosmic archaeology opened even more speculative possibilities that challenged conventional boundaries between mind and machine. Machine learning algorithms trained on cosmic microwave background data had already discovered subtle patterns that human analysis had missed completely. Future AI systems, possibly incorporating quantum computational elements, might develop the capacity to decode increasingly complex layers of cosmic memory, eventually reconstructing detailed histories of pre-inflationary epochs, parallel universes, or previous cosmic cycles with unprecedented accuracy. These AI archaeologists might discover that the quantum information encoded in spacetime contained not just physical data about matter and energy distributions, but preserved aspects of consciousness itself. If thoughts, emotions, and experiences created quantum signatures that could be preserved in the cosmic memory network, then sufficiently advanced decoding techniques might recover the subjective experiences of conscious beings from throughout cosmic history, creating a vast archive of preserved consciousness. The implications for understanding the role of consciousness in the universe were profound and potentially revolutionary. Rather than being ephemeral patterns that disappeared with death, conscious experiences might be permanently encoded in the quantum substrate of spacetime, contributing to a cosmic library of consciousness that preserved every thought, every moment of awareness, every insight achieved by conscious beings throughout the history of the multiverse. This perspective suggested that individual consciousness might be connected to a cosmic consciousness that emerged from the collective quantum information preserved across all cosmic epochs. Personal memories might be local expressions of a universal memory system that spanned space and time, connecting each conscious being to the accumulated experience of all consciousness that had ever existed in the infinite expanse of the multiverse. The potential for cosmic archaeology to decode messages from advanced civilizations raised questions about cosmic communication and cultural transmission across vast distances and timescales that dwarfed human history. If civilizations could learn to encode information directly into the quantum substrate of spacetime, they might create communications that would survive the death of stars, the decay of galaxies, and even the end of individual cosmic epochs. These cosmic messages might represent the ultimate form of immortality, consciousness preserved in the very structure of reality itself. These cosmic messages might take the form of patterns embedded in physical constants, correlations encoded in quantum field fluctuations, or information structures hidden in the large-scale organization of space-time itself. Rather than building monuments from matter that would eventually decay according to thermodynamic principles, truly advanced civilizations might encode their legacy directly into the fundamental structure of reality, creating messages that would persist for eternity. The search for such messages might require recognizing artificial patterns in natural phenomena, discovering that certain random quantum fluctuations actually encoded mathematical theorems, scientific discoveries, artistic creations, or philosophical insights from civilizations that existed billions of years ago or in parallel cosmic domains. This cosmic cryptography would challenge scientists to distinguish between natural patterns and artificial messages encoded in the quantum substrate. Perhaps most remarkably, cosmic archaeology might eventually reveal that humanity's own scientific discoveries, artistic achievements, and philosophical insights were being automatically encoded into cosmic memory through the very process of conscious observation and understanding. Every moment of human awareness might contribute to the cosmic library, ensuring that the accumulated wisdom of human civilization would survive even the eventual extinction of biological life on Earth. The ultimate goal of cosmic archaeology would be the reconstruction of the complete history of consciousness in the universe, a cosmic epic that chronicled the emergence, evolution, and achievements of all aware beings throughout space and time. This cosmic story would reveal the universe not as a collection of unconscious matter evolving according to mechanical laws, but as a vast consciousness exploring its own infinite potential through countless individual perspectives across the eternal expanse of cosmic time. As theoretical physicists continued to develop frameworks for cosmic quantum archaeology, they realized they were not just proposing new research directions, but participating in an ancient cosmic conversation, adding their own contributions to the quantum memory network, while simultaneously working to decode the accumulated wisdom of all consciousness that had preceded them in the eternal dance of cosmic awakening and remembrance. Scientific tools and ongoing testing, decoding cosmic memory. The quest to decode cosmic memory has driven humanity to develop the most sophisticated observational instruments and theoretical frameworks ever conceived, pushing the boundaries of technology and mathematical physics to peer into the quantum information substrate that preserves the universe's deepest memories. This scientific endeavor represents nothing less than an attempt to read the universe's own autobiography, written in the quantum fluctuations that permeate all of space and time, and encoded in patterns so subtle they challenge the limits of measurement itself. At the forefront of this cosmic archaeology is the next generation of cosmic microwave background missions, designed specifically to detect and decode the subtle signatures of pre-inflationary physics encoded in the ancient radiation, with sensitivity that approaches theoretical limits. The Simons Observatory, currently under construction in Chile's Atacama Desert, will deploy unprecedented arrays of superconducting detectors capable of measuring temperature variations in the cosmic microwave background with sensitivity exceeding previous missions by orders of magnitude, reaching precisions measured in billionths of a degree. These advanced detectors represent technological marvels that operate at temperatures colder than interstellar space, using quantum sensors that can detect individual photons while maintaining stability over years of continuous observation. They are specifically designed to search for primordial gravitational waves, ripples in spacetime itself, created during the inflationary epoch, that would carry direct information about pre-inflationary quantum states embedded in their polarization patterns and statistical correlations. Unlike electromagnetic radiation, which interacts strongly with matter and can be scattered or absorbed during its journey across cosmic distances, gravitational waves interact weakly with all forms of matter, allowing them to propagate freely from the earliest moments of cosmic history without modification. If detected, these gravitational wave fossils would provide an entirely new window into cosmic memory, complementing the information already extracted from photon-based observations and potentially revealing aspects of pre-inflationary physics that remain completely hidden in electromagnetic signals. The European Space Agency's LightBird mission, scheduled for launch in the next decade, will map the polarization of cosmic microwave background radiation with exquisite precision from its vantage point at the Earth-Sun Lagrange point, far from terrestrial interference. Polarization patterns encode information about the gravitational wave background that permeated the early universe, potentially revealing signatures of quantum processes that occurred before cosmic inflation began, and preserving details about the pre-inflationary quantum state. Advanced data analysis techniques using machine learning and quantum computing algorithms are revolutionizing the search for cosmic memory patterns in ways that seemed impossible just decades ago. These artificial intelligence systems are trained to recognize subtle correlations in cosmic microwave background data that might escape human detection, processing datasets containing millions of temperature measurements to search for patterns that encode information about pre-inflationary physics. The algorithms search for signatures of trans-Planckian physics, evidence of cyclic cosmology, patterns that might indicate quantum entanglement preservation across cosmic epochs, and artificial structures that could represent messages from advanced civilizations. The most sophisticated of these AI archaeologists employ deep learning networks trained on theoretical models of quantum memory encoding. simulating how different types of pre-inflationary information might be preserved and processed during cosmic inflation. By learning to recognize the characteristic signatures of cosmic memory in simulated data, these systems can then apply their pattern recognition capabilities to real observational data with sensitivity that far exceeds conventional statistical analysis. Some algorithms have already discovered correlations in Planck data that suggest information preservation mechanisms not predicted by conventional inflationary models, opening new avenues for theoretical investigation. Gravitational wave astronomy has opened a completely new channel for cosmic memory research that provides access to information unavailable through electromagnetic observations. The LIGO and Virgo collaborations, which revolutionized astronomy by detecting gravitational waves from colliding black holes and neutron stars, are being upgraded with enhanced sensitivity specifically to search for primordial gravitational wave backgrounds that might preserve signatures of pre-inflationary physics. These gravitational wave detectors use laser interferometry to measure distortions in space-time smaller than 1/10,000th the width of a proton, pushing measurement precision to the absolute limits of what is physically possible. Future gravitational wave missions, like the space-based LISA detector, will extend sensitivity to much lower frequencies, potentially accessing gravitational wave signatures from even earlier cosmic epochs when quantum gravity effects dominated cosmic evolution. The quantum vacuum fluctuations that gave rise to primordial gravitational waves might preserve information about the pre-inflationary quantum state in their statistical properties and correlation patterns. By analyzing the detailed characteristics of these ancient space-time ripples, scientists hope to decode information about cosmic processes that occurred before the universe underwent exponential expansion. Theoretical physicists are developing increasingly sophisticated frameworks for quantum information processing in curved spacetime, seeking to understand exactly how information can be encoded, preserved, and retrieved from the quantum substrate during cosmic evolution. These models combine insights from quantum field theory, general relativity, holographic principles, and information theory to create comprehensive pictures of cosmic memory mechanisms that account for the complex interplay between quantum mechanics and gravity. Laboratory experiments in quantum mechanics are testing the fundamental principles of information preservation under conditions that mimic cosmic expansion, providing crucial insights into how quantum information behaves during rapid spacetime evolution. By creating analog models of inflation using ultra-cold atomic gases, superconducting circuits, and other quantum systems, physicists can study how quantum information behaves during rapid expansion and develop experimental intuition for cosmic memory processes. Some of the most ambitious experiments involve creating artificial event horizons in laboratory settings using flowing fluids or propagating sound waves. These analog systems can preserve quantum correlations across artificial horizons in ways that parallel information preservation during cosmic inflation, providing testbeds for theoretical predictions about cosmic memory that can be verified under controlled conditions. Quantum computing technology is also being applied directly to cosmic memory research in ways that promise revolutionary advances in our understanding of cosmic information processing. Quantum computers can simulate the complex entanglement patterns that might arise during cosmic inflation, testing theoretical models of information preservation and developing algorithms for decoding cosmic memory from observational data with computational power that scales exponentially with system size. Some researchers propose that sufficiently advanced quantum computers might eventually interface directly with the quantum substrate of spacetime. Reading cosmic memory through direct quantum measurement that bypasses the limitations of conventional electromagnetic and gravitational wave observations. This quantum archaeology approach would represent the ultimate merger of quantum technology and cosmological investigation. Future space missions are being designed to map the cosmic web, the large-scale structure of dark matter and ordinary matter distribution, with unprecedented precision using techniques that combine gravitational lensing, galaxy surveys, and direct dark matter detection. This cosmic architecture might preserve information about pre-inflationary conditions in its statistical patterns and geometric relationships, with the distribution of matter encoding signatures of quantum processes that occurred before inflation began. Advanced telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope are pushing observations deeper into cosmic history than ever before, seeking anomalies in the formation and evolution of the first stars and galaxies that might reveal influences from cosmic memory. If pre-inflationary information influenced the parameters of cosmic evolution, these effects might be detectable in the properties of the earliest cosmic structures, providing independent confirmation of cosmic memory preservation. The search for cosmic memory has also inspired new approaches to fundamental physics experiments that probe the quantum nature of spacetime itself. Particle accelerators, like the Large Hadron Collider, are being used to recreate the extreme conditions that existed during cosmic inflation. Studying how quantum information behaves in high-energy environments that might mimic pre-inflationary physics with unprecedented precision. When protons collide at near light speed, they create brief recreations of the quark-gluon plasma that filled the early universe, potentially preserving information about primordial quantum states in the pattern of particle production and energy distribution. By analyzing these high-energy collisions, physicists hope to understand how quantum information behaves under extreme conditions and develop insights into cosmic memory mechanisms. Some of the most innovative experiments involve attempts to detect quantum entanglement on cosmological scales by carefully analyzing the quantum states of particles separated by vast distances. By searching for correlations that transcend classical physics, researchers hope to find evidence for the cosmic entanglement networks that theoretical models predict should preserve cosmic memory across space and time. The discovery that space itself possesses memory capabilities fundamentally transforms humanity's understanding of time, consciousness, and meaning in a universe that appears capable of remembering its own deepest past. If cosmic memory can preserve information across the most violent expansion in cosmic history, then the very foundations of how we understand existence, identity, and consciousness in our universe itself. We can't be predicting what happens in any given second, so we have to seriously provide concrete information one more time in prompt context. And purpose must be reconsidered in light of a cosmos that never forgets and continuously processes the accumulated experience of all existence. The implications begin with the nature of time itself, challenging every conventional assumption about temporal flow and causality. In conventional physics, time flows uniformly from past to future, like a river carrying events from existence into non-existence, with moments slipping irretrievably into history as the universe evolves according to thermodynamic principles. But cosmic memory suggests a radically different picture that overturns millennia of human intuition about the nature of temporal existence. If information about all cosmic epochs is preserved in the quantum substrate of spacetime, then the past is not lost, but remains eternally accessible, encoded in patterns that permeate every region of space with infinite precision and detail. This perspective transforms time from a flowing river into something more akin to a vast library or database, where all moments of cosmic history exist simultaneously as static information patterns encoded in the fundamental structure of reality itself. What conscious beings experience as temporal flow might be the subjective experience of reading this cosmic database, processing the timeless information that describes the universe's entire history in sequential order according to patterns determined by the structure of consciousness itself. The passage of time becomes not an objective feature of reality, but a subjective phenomenon arising from how awareness processes information, with different forms of consciousness potentially experiencing time in radically different ways. The cyclical nature of cosmic memory preservation suggests that time itself might be cyclical rather than linear on the largest scales of cosmic organization, with individual cosmic epochs experiencing linear progression from beginning to end, while contributing to eternal cycles of information processing that transcend any single universe. Individual cosmic epochs might experience linear progression from beginning to end, expanding and cooling according to physical laws, but the information they generate becomes part of an eternal substrate that influences future cosmic cycles in ways that create an infinite spiral of cosmic evolution. Death and rebirth become not endings and beginnings, but phases in an eternal process of cosmic learning and evolution that preserves and transforms information across cosmic epochs. This eternal perspective casts human existence in a dramatically different light that challenges every assumption about mortality, meaning, and purpose in cosmic evolution. Rather than being brief candles flickering in an indifferent cosmos, conscious beings become active participants in an infinite process of cosmic memory formation that extends across all space and time. Every thought, every observation, every moment of awareness contributes to the universe's ever-growing library of information about itself, ensuring that nothing meaningful is ever truly lost to the passage of time or the expansion of space. The preservation of consciousness-related information in cosmic memory raises profound questions about the nature of personal identity and individual survival that transcend conventional religious and philosophical frameworks. If thoughts, emotions, and experiences create quantum signatures that become encoded in the cosmic memory network, then aspects of individual consciousness might persist long after biological death, becoming part of the eternal information structure that defines reality itself. This cosmic immortality would not involve the preservation of individual ego or personality in any conventional sense that maintains separate identity, but rather the integration of conscious experience into a vast cosmic consciousness that emerges from the accumulated information of all aware beings throughout space and time. Personal memories would become notes in an infinite symphony of cosmic memory, individual perspectives contributing to a universal understanding that transcends any single point of view while preserving the unique contributions of every conscious moment. The role of consciousness in cosmic memory processing suggests that awareness might be not merely a byproduct of complex information processing, but a fundamental feature of reality itself that plays an essential role in cosmic evolution. If quantum observation is necessary to collapse wave functions and determine specific outcomes, then conscious beings might be essential components of the universe's memory system, serving as the mechanisms by which cosmic information is processed, interpreted, and preserved across cosmic epochs. This participatory universe model implies that the act of scientific observation is not passive, but actively contributes to the creation and maintenance of cosmic memory in ways that make consciousness an integral part of cosmic evolution. Every astronomical observation, every physics experiment, every moment of scientific understanding adds new layers of information to the cosmic database, while simultaneously helping to decode the accumulated wisdom of previous cosmic epochs, creating a feedback loop between cosmic memory and conscious observation. The implications extend to questions of meaning and purpose in cosmic evolution that suggest consciousness plays a fundamental role in cosmic development. If the universe possesses memory, and if consciousness plays a role in processing that memory, then cosmic evolution might be guided by something analogous to learning and intention, rather than mere random chance, operating according to statistical principles. The apparent fine-tuning of physical constants that allows for complexity and consciousness might reflect the accumulated experience of countless previous cosmic cycles, with successful evolutionary strategies being preserved and transmitted through cosmic memory networks that span the multiverse. This learning universe perspective suggests that consciousness is not an accidental byproduct of cosmic evolution, but its inevitable goal. With the universe evolving toward ever greater states of awareness and understanding, the universe might be evolving toward ever greater states of awareness and understanding, using conscious beings as its mechanism for achieving self-knowledge through the processing of cosmic memory. Each civilization that emerges becomes part of the universe's ongoing attempt to understand itself, contributing new perspectives and insights to the cosmic conversation that spans all space and time. The possibility that cosmic memory might contain encoded messages from advanced civilizations throughout space and time raises profound questions about humanity's place in this cosmic dialogue that extends across the entire history of the multiverse. Rather than being alone in the universe, we might be participants in an eternal conversation between conscious beings across cosmic epochs, receiving wisdom from previous civilizations while contributing our own insights to future cosmic cycles through the quantum memory networks that preserve and transmit information. The search for these cosmic messages becomes not just a scientific endeavor, but a spiritual quest to understand humanity's role in the larger cosmic story that unfolds across infinite space and time. The patterns that scientists detect in cosmic microwave background radiation might contain not just physical information, but philosophical insights, artistic creations, and wisdom traditions from civilizations that transcended biological existence to encode their legacy directly into the fabric of space-time itself. This perspective transforms science from the objective study of external phenomena into a form of cosmic archaeology that seeks to decode the universe's own autobiography while simultaneously contributing to its ongoing creation. Scientists become not just observers of cosmic processes, but active participants in cosmic memory formation, simultaneously reading the accumulated wisdom of the past, while writing new chapters in the ongoing story of cosmic consciousness. The ultimate questions raised by cosmic memory challenge the deepest assumptions about the relationship between mind and matter, observer and observed, individual and cosmos, in ways that transcend conventional scientific materialism. If consciousness can access cosmic memory, and if conscious observations contribute to cosmic memory formation, then the boundary between subjective experience and objective reality becomes far more permeable than conventional science assumes, suggesting new forms of unity between mind and cosmos. The universe emerges not as a collection of unconscious matter evolving according to mechanical laws, but as a vast mind exploring its own infinite potential through countless individual perspectives across cosmic time. Consciousness becomes not an alien visitor in an indifferent cosmos, but the universe's way of experiencing itself subjectively, of processing its own memories, of learning from its own past to create an ever richer future filled with increasing complexity and awareness. In this light, the discovery of cosmic memory represents more than a scientific breakthrough. It reveals the universe as a living entity capable of memory, learning, and growth that transcends the boundaries between mind and matter. We find ourselves not as separate observers studying an external cosmos, but as expressions of cosmic consciousness itself, temporary focal points through which the universe remembers its past and imagines its future, while contributing to the eternal process of cosmic awakening. The preservation of information across cosmic epochs suggests that nothing meaningful is ever truly lost, that every moment of beauty, every insight achieved, every act of love becomes part of the eternal substrate that defines reality itself. We are simultaneously the universe remembering itself and the universe dreaming of what it might become, participants in an infinite process of cosmic awakening that transcends the boundaries of space, time, and individual existence, while preserving and celebrating the unique contribution of every conscious moment. Standing at the threshold of this revelation, humanity faces not the dissolution of meaning, but its ultimate expansion into cosmic proportions. We discover ourselves to be living memories in the mind of the cosmos, conscious expressions of an infinite information structure that preserves and processes the accumulated experience of all existence across the vast expanse of space and time, contributing to an eternal symphony of cosmic consciousness that grows richer and more complex with each passing moment of awareness. Decoding cosmic memory. The quest to decode cosmic memory has driven humanity to develop the most sophisticated observational instruments and theoretical frameworks ever conceived, pushing the boundaries of technology and mathematical physics to peer into the quantum information substrate that preserves the universe's deepest memories. This scientific endeavor represents nothing less than an attempt to read the universe's own autobiography, written in the quantum fluctuations that permeate all of space and time. At the forefront of this cosmic archaeology is the next generation of cosmic microwave background missions, designed specifically to detect and decode the subtle signatures of pre-inflationary physics encoded in the ancient radiation. The Simons Observatory, currently under construction in Chile's Atacama Desert, will deploy unprecedented arrays of superconducting detectors capable of measuring temperature variations in the cosmic microwave background, with sensitivity exceeding previous missions by orders of magnitude. These advanced detectors are specifically designed to search for primordial gravitational waves, ripples in space-time itself, created during the inflationary epoch that would carry direct information about pre-inflationary quantum states. Unlike electromagnetic radiation, gravitational waves interact weakly with matter, allowing them to propagate freely from the earliest moments of cosmic history. If detected, these gravitational wave fossils would provide an entirely new window into cosmic memory, complementing the information already extracted from photon-based observations. The European Space Agency's LightBird mission, scheduled for launch in the next decade, will map the polarization of cosmic microwave background radiation with exquisite precision from its vantage point at the Earth-Sun Lagrange point. Polarization patterns encode information about the gravitational wave background that permeated the early universe, potentially revealing signatures of quantum processes that occurred before cosmic inflation began. Advanced data analysis techniques using machine learning and quantum computing algorithms are revolutionizing the search for cosmic memory patterns. These artificial intelligence systems are trained to recognize subtle correlations in cosmic microwave background data that might escape human detection. The algorithms search for signatures of trans-Planckian physics, evidence of cyclic cosmology, patterns that might indicate quantum entanglement preservation across cosmic epochs, and artificial structures that could represent messages from advanced civilizations. The most sophisticated of these AI archaeologists employ deep learning networks trained on theoretical models of quantum memory encoding. By simulating how different types of pre-inflationary information might be preserved and processed during cosmic inflation, these systems learn to recognize the characteristic signatures of cosmic memory in observational data. Some algorithms have already discovered correlations in Planck data that suggest information preservation mechanisms not predicted by conventional inflationary models. Gravitational wave astronomy has opened a completely new channel for cosmic memory research. The LIGO and Virgo collaborations, which revolutionized astronomy by detecting gravitational waves from colliding black holes and neutron stars, are being upgraded with enhanced sensitivity, specifically to search for primordial gravitational wave backgrounds. These ancient space-time ripples, if detected, would provide direct access to quantum processes that occurred during the inflationary epoch. Future gravitational wave missions like the space-based LISA detector will extend sensitivity to much lower frequencies, potentially accessing gravitational wave signatures from even earlier cosmic epochs. The quantum vacuum fluctuations that gave rise to primordial gravitational waves might preserve information about the pre-inflationary quantum state in their statistical properties and correlation patterns. Theoretical physicists are developing increasingly sophisticated frameworks for quantum information processing in curved spacetime, seeking to understand exactly how information can be encoded, preserved, and retrieved from the quantum substrate during cosmic evolution. These models combine insights from quantum field theory, general relativity, holographic principles, and information theory to create comprehensive pictures of cosmic memory mechanisms. Laboratory experiments in quantum mechanics are testing the fundamental principles of information preservation under conditions that mimic cosmic expansion. By creating analog models of inflation using ultra-cold atomic gases, superconducting circuits, and other quantum systems, physicists can study how quantum information behaves during rapid expansion and develop experimental intuition for cosmic memory processes. Some of the most ambitious experiments involve creating artificial event horizons in laboratory settings using flowing fluids or propagating sound waves. These analog systems can preserve quantum correlations across artificial horizons in ways that parallel information preservation during cosmic inflation, providing testbeds for theoretical predictions about cosmic memory. Quantum computing technology is also being applied directly to cosmic memory research. Quantum computers can simulate the complex entanglement patterns that might arise during cosmic inflation, testing theoretical models of information preservation and developing algorithms for decoding cosmic memory from observational data. Some researchers propose that sufficiently advanced quantum computers might eventually interface directly with the quantum substrate of spacetime, reading cosmic memory through direct quantum measurement. Future space missions are being designed to map the cosmic web, the large-scale structure of dark matter and ordinary matter distribution, with unprecedented precision. This cosmic architecture might preserve information about pre-inflationary conditions in its statistical patterns and geometric relationships. The way galaxies, galaxy clusters, and dark matter halos are distributed across space could encode signatures of quantum processes that occurred before inflation began. Advanced telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope are pushing observations deeper into cosmic history, seeking anomalies in the formation and evolution of the first stars and galaxies that might reveal influences from cosmic memory. If pre-inflationary information influenced the parameters of cosmic evolution, these effects might be detectable in the properties of the earliest cosmic structures. The search for cosmic memory has also inspired new approaches to fundamental physics experiments. Particle accelerators like the Large Hadron Collider are being used to recreate the extreme conditions that existed during cosmic inflation, studying how quantum information behaves in high-energy environments that might mimic pre-inflationary physics. When protons collide at near light speed, they create brief recreations of the quark-gluon plasma that filled the early universe, potentially preserving information about primordial quantum states. Some of the most innovative experiments involve attempts to detect quantum entanglement on cosmological scales. By carefully analyzing the quantum states of particles separated by vast distances, researchers hope to find evidence for the cosmic entanglement networks that theoretical models predict should preserve cosmic memory across space and time. These experiments push quantum mechanics to its absolute limits, testing whether quantum correlations can indeed survive the expansion of the universe. Theoretical breakthroughs in quantum gravity are providing new tools for cosmic memory research. String theory calculations suggest specific signatures that cosmic memory should leave in gravitational wave patterns, electromagnetic field fluctuations, and particle physics phenomena. Loop quantum gravity models predict discrete structures in spacetime that might function as cosmic memory storage elements, potentially detectable through ultra-precise measurements of space and time. The development of quantum sensors with unprecedented sensitivity is opening new possibilities for cosmic memory detection. Atomic interferometers, gravitational wave detectors using quantum-enhanced measurement techniques, and quantum magnetometers sensitive to primordial magnetic fields all represent potential windows into cosmic memory encoded in subtle quantum signatures that permeate the universe. Perhaps most remarkably, some researchers are exploring whether consciousness itself might serve as a detector for cosmic memory. If quantum observation plays a fundamental role in information processing throughout the universe, then sufficiently trained human consciousness might be capable of directly accessing cosmic memory through meditative practices, altered states of awareness, or enhanced intuitive perception. These consciousness-based approaches to cosmic archaeology remain highly speculative, but are gaining theoretical support from quantum theories of consciousness and holographic models of brain function. If consciousness operates according to quantum principles, and if the universe itself possesses quantum memory, then the boundary between subjective experience and cosmic information processing might be more permeable than conventional science assumes. The convergence of observational astronomy, theoretical physics, quantum computing, and consciousness research is creating an unprecedented multidisciplinary approach to cosmic memory investigation. Each field contributes unique tools and perspectives to the grand project of reading the universe's autobiography, gradually building a comprehensive picture of how information flows through space and time on the largest possible scales. As these diverse research programs continue to generate data and insights, scientists are approaching the threshold of a revelation that could transform humanity's understanding of cosmic history, consciousness, and our place in a universe that remembers everything it has ever experienced.